So one thing to point out about this, when you start looking at SANs themselves, understanding the topology that's associated with storage area networking. So in this particular example topology, the back of this SAN controller has 4 individual 10 gig ports. So you'll see that controller A has 4 10 gig ports and controller B has 4 10 gig ports. And they're actually implemented using an alternate IP subnet scheme for connectivity from servers all the way down to the SAN to provide that resilient storage. One of the questions that's often asked is, how many ports do I need to actually connect on the back of my SAN? I may only be pushing 1 or 2 gigs of traffic. Do I need to connect all 8 ports? And the answer is yes. You're not going to get anywhere near 80 gigs of actual traffic throughput. But remember, it's not about the traffic throughput. It's about the buffering. It's about the contention. And the more servers that you add to this, the more chance is that you're going to create that port contention that resides or relies on that deep buffering to prevent that you don't get packet loss. So in other words, the number of ports, as you increase from 1 or 2 ports and you connect 1, 2, 3, 4, 5, 6, all the way up to 8 ports, the more ports that you connect on the back of that SAN, the more targets you give for the actual switch fabric to create an environment where it's not contending multiple servers to communicate with multiple ports on that SAN. So the more that you light up, the less contention you're going to create, the less chance at the network switch level that you're going to exhaust those buffers, and the less chance in that centralized storage that you're actually going to result in some type of data loss paradigm, meaning that you're going to get dropped packets or you're going to get an issue with corrupted video. So rule of thumb with this, regardless of the number of servers, it's always best practice to connect all of your iSCSI ports on the back and allow those servers to load balance across those available iSCSI ports. Here's a blow up for the back of a particular SAN showing what you've got. And the 2 controllers here, you can see that you've got, in this case, using fiber channel. So it's got 4 fiber channel connections on the left side, 4 fiber channel connections on the right side. You always have a management port associated with each controller that you can use in to manage the actual SAN itself, as well as you are going to have SAS connectors for expansion bays. So while these SANs are becoming incredibly powerful with respect to the amount of data that they can store, you can actually create expansion boxes or expansion servers on the back end of this for storage that allow you to push this into the multi-petabyte range. Here's an example of different ways you can connect it up, but in the case of these particular platforms, you'll typically have 1 controller port and up to 4 expansion boxes using or leveraging SAS connectivity to actually allow you to expand the storage. This allows a site to start with a particular amount of storage, and as they need to add more storage, they're not actually purchasing more controllers, they're not making more connectivity ports or connectivity port connections into the network. They're simply adding expansion storage as the retention needs either expand or grow. When you look at optimizing SAN storage, there are a couple of ways you can go about this. The majority of clients that we deal with typically use either a RAID 6 environment. Some will go RAID 10 or RAID 50 in some cases. But in most cases, people use a RAID 6, and that may or may not include the implementation of hot spares. The idea of a hot spare means that you have drives that aren't being recorded to, but in the event that you have a failure of a drive within the RAID 6, that hot spare will actually take the place of that failed drive without intervention or any kind of configuration having to be done to actually recover that. In addition to doing RAID technologies, you also have the ability to support erasure-coded based storage. So in the particular product that we use, it's called ADAPT technology, but erasure-coded storage is a much, much more complicated but very powerful way to stripe the data across the control sets. So in a traditional RAID-based storage for a SAN, I may go in and divide up 14 drive sets across that particular 84 bay box. I may break the 84 drives down into groups of 12. And each one of those create a RAID 6, and those servers create their iSCSI connections and mappings back into multiple RAID 6 arrays. The problem with that is each one of those RAID 6 arrays are actually created as an independent storage point. meaning that the maximum amount of I/O throughput I can get out of that is a subset of the number of drive sets that are in there. So if I have 12 drives, the cumulative I/O capacity of those 12 drives minus the overhead associated with the redundancy is going to establish my I/O rate that I can get to that particular RAID controller or that particular linear drive set within the RAID array. When you take an adapt approach, every drive within the box becomes part of a common erasure-coded storage, meaning that as opposed to having 12 drives that you can determine what your IOPS are going to be, you may leverage 84 or more drives simultaneously for all data sets. By activating more of the drives, you actually create a much higher I/O capacity that you can put through that SAN, and you also create a more fault-tolerant and faster recovering solution.